this module, we're going to look at the nature of fracturing in carbonates, where we have structures ranging from joints, through faults, through shears, all of which can contribute to the flow characteristics, the permeability in ancient carbonate reservoirs, where much of the original depositional and early diagenetic porosity is greatly reduced. And yet, most giant oil fields producing from carbonates have some degree of fracture. The course is made up of 6 video chapters. In this first chapter, we're going to look at the conceptual nature of the various structures of fractures and faults, focusing on those features as they influence carbonates and the flow capacities in carbonates. The next looks at the types of fractures with both regional and local variations in the density or the intensity of fracturings, and how the origins of those fractures and their timing ties back to the rock properties, especially the degree of dolomite versus limestone in that host carbonate. Following that, we'll look at faulted fracture zones, the extent, the origins, and the influences of various types of fault damage and different styles of shearing on the flow capacity and the nature of the distribution of fracture intensities and preferential flow directions in a subsurface carbonate. That's because fractures make for dual porosity and permeability systems, where the fractures contribute to the nature of the flow. Following that, we'll have a look at how we separate natural fractures from sampling artifacts, and we'll finish that off with a series of examples that illustrate the influence of various fracture types using the Nelson classification, how they influence flow character in both giant fields and ore deposits. The general reading texts for this course are focused around an excellent book on structural geology by Fossen, the second edition being published in 2016. We'll also utilise the Atlas of Natural and Induced Fractures in Core, published by Lawrence and Cooper back in 2018. We'll draw on some of the notions of touching versus isolated vugs in fracture systems and their flow character from the excellent text by Lucia, published back in 2007. And we looked at this also in quite a bit of detail, and we looked at porosity in the carbonate diagenesis discussion. And we'll also draw quite heavily upon the notions and the ideas summarised in Nelson in his geologic analysis of naturally fractured reservoirs, which was published back in 2001. In addition to those 4 major general texts, we'll also draw on the various papers that are referenced in the various slides and illustrations as we go through this discussion of fracturing on carbonate producibility. Let's start off with a little bit of Structural Geology 101, and we'll have a look at the nature of cracks in a rock and the various definitions we use. A fracture is defined as a surface of rupture of physical or physiochemical bonds. Fractures can range in magnitude from submicroscopic up into kilometre scale systems. Joints are a form of fracture. They're a set of parallel fractures that have no detectable displacement along the fracture surface. Groups of joints with the same orientation we define as joint sets. A fault is a fracture with detectable displacement, and we can have both extensional and shear faults, and we'll discuss those different styles a little later in the course. A fissure is a fracture where the walls have been significantly dissolved, typically by acidic waters in a carbonate, and so there's greater separation of the walls of the fracture, typically in a direction that's normal to the plane of that fracture. There are shear fractures, there are extension fractures, which are also joints, and there are extension fractures which have been widened, which we'll define as fissures. Here are a set of parallel joint sets in the Utica Shale. Here are a set of more complex joint sets, the UK. Here is an extensional fault set with obvious displacement with that down-dropped conjugate block. And then here are a set of open fissures in a castifying limestone, where the original joint sets have been opened up via the process of dissolution and linked by that process of dissolution. This type of fissuring dominates in many near-surface outcrops in carbonates, but it can also form in the subsurface in bathyphreatic settings, as we discussed in the carbonate diagenesis setting. It's not a form that is common in sandstone reservoirs. Open joints and fractures in carbonates serve as important subsurface pathways for fluid flow, both water and oil, and so that of course makes them of prime interest to both hydrologists and petroleum geologists. and indirectly to economic geologists looking at access of metalliferous fluids to prepared ground in carbonate hosts in some types of base metal and copper gold deposits. So the presence of joints will enhance the flow and storage of groundwater and hydrocarbons. Joints, if they are subjected to acidic waters, can also contribute to the development of fissures and caverns in a variety of carbonates, both limestones and dolomites. Here's a variety of natural fractures, and you can clearly see that not all those fractures are open. We've got slicken sites on fractures, we've got cemented fractures, we've got open fractures, and we've got the development of open vugs in fractures. All fractures and joints are tied to a compression response. By definition, the sides of any joint is a fracture where the sides are moving away from each other but don't slide past each other. If we see displacement from either side of the fracture, that by definition becomes a fault. The forces that are producing joints are literally pulling the rock apart. Now, forces that pull something apart, a civil engineer describes as tensile forces. But as geologists, we work with rocks that are nearly always in varying states of compression. So true tensional forces are relatively uncommon in the subsurface. And in effect, we usually describe the tensional force as actually being the force of least compression of the three sigma 1, sigma 2, sigma 3 stress parameters. So geologists describe the tensional force as the force of least compression, sigma 3, with the maximum compressive stress being defined as sigma 1. The direction of least compressive stress, sigma 3, will be the direction in which extension occurs, tensional extension if you like. So the joint or fracture will open up as the sides move away from each other, sigma 3. So we form joints, we form extension fractures, and we can also infill some of those extension fractures with cements, typically in a carbonate with calcite or dolomite cements, to make veins. The direction of an extensional joint or an extensional fracture is typically perpendicular to the direction of the least compressive force, sigma 3, while the direction of the massive compressional force, sigma 1, induced from overburden stress, burial compaction, or if tectonic stresses are applied from the direction of maximum tectonic stress, will be orthogonal to the least compressive stress direction. In horizontally bedded strata, the least compressive stress direction will be parallel to the bedding. It's typically parallel to the direction of stylolite or precious solutional. We make the general observation, and we'll keep this in mind throughout this discussion of fractures, that extensional fractures and joints form perpendicular to sigma 3, while shear fractures typically form at a 20 to 30 degree angle to sigma 1. We went into this in a lot more detail in the salt tectonics course, where we did a detailed discussion of the separation of ductile versus brittle responses, focusing there on salt, but the same criteria also hold, as we've summarized here, for carbonates and for any sediment. In any subsurface environment, depending on the confining pressure or the confining stress, we will see brittle to ductile responses. In the diagram, sigma 1 is greater than sigma 2, which will make it equal to sigma 3 in this situation, and we see a response that goes from brittle behavior into a conjugate transitional behavior, where we see fractures forming in both scenarios, into a ductile situation where we don't form fractures. The rock is responding in a ductile fashion. We saw in the halotectonics course how salt nearly always responds in a ductile fashion, whereas other sediments, limestones, dolomites, sandstones, shales, tend to respond in a much more brittle fashion, certainly in the shallower parts of the burial diagenetic realm. So dolostone, limestones, some chalks, along with some silica-cemented sandstones and cherts, will act brittly at Earth's surface and shallow burial temperatures and pressures relevant to hydrocarbon reservoirs. Whereas we'll see ductile and plastic behaviour. In the same diagenetic temperature and pressure realm, the rocks are behaving in a more ductile fashion, as we see in shales, mud rocks, salt, other forms of evaporites, marls, and clay-rich chalks. And this is why these ductile rocks make such excellent seals. And certainly if we have an evaporite seal over a carbonate, the carbonates will always respond in a brittle fashion, where the evaporites will always respond in a ductile fashion, maintaining their seal integrity. All rocks at higher temperatures and confining pressures will respond in a ductile fashion, so that ductile fractures and also some forms of deformation band occur under those higher confining pressure and temperature conditions. So how does a fracture open? How does it propagate? Well, there are three main modes of fracture propagation. Mode 1, which is the most common type of opening in the diagenetic realm, is called the tensile mode, where the tensile stress, the direction of least compressive stress, is perpendicular to the cracked surface. This is how most rocks fracture in the subsurface. Mode 2 is a sliding or in-plane shear response, where the shear stress is parallel to the fracture plane and is perpendicular to the propagating front, as it was in Mode 1. Whereas in Mode 3, which is sometimes called the tearing or antiplane shear response of fracture opening, the shear stress is parallel to both the fracture plane and the crack front. So Mode 1 creates extensional fractures, Mode 2 creates shear fault responses, and Mode 3 creates tear fault responses. Most of the time in the subsurface, in the brittle rocks that we're looking at as potential reservoir rocks, the carbonates, the limestones and the dolomites, Mode 1 is the most common type of fracture. In that diagenetic realm, the rock's tensile strength is lower than its shear strength. Once we have a fracture propagating in a rock, we have the potential to open that rock up to fluid flow and to join up any matrix porosity into a fracture-drained permeability. Open fractures in the subsurface in carbonates are fluid conduits. If we have dissolution of the carbonate rock in that subsurface realm, some type of acidic solution, it could be meteoric waters, it could be acidic waters coming off a dissolving evaporite unit, or coming off of the catagenic stage in a shale, those opening fractures will be a major source of heterogeneity in the reservoir property of that carbonate reservoir at all scales, from the microscopic to the macroscopic, where the dissolution intensity is related to the flow rate of that undersaturated fluid through the fissures. The variation, the reservoir's heterogeneity, is going to be closely related to varying diagenetic intensities, both depositional residual and partially preserved early diagenetic differentiations. And it's also going to be related to when the fractures join up, to the timings of fracture connectivity, when those fractures cement up and lose some of that permeability. And at the same time, that's going to relate back to the bed matrix permeability, which will also be evolving in the subsurface, as we discussed in the heterogeneities associated with carbonate diagenesis. So here in the Alps, we can see fracture tensity is related to lithology, those carbonate units showing obvious cross-bedding fractures, where the more ductile units, the shales, are not as fractured. When we look at carbonates, we have to discuss, are the fractures isolated, they're not joined up, or are they touching? The fractures are joined up. This ties back to our discussion of Lucia's classification of open versus touching vugs. So permeability in a fractured carbonate reservoir will be determined by a combination of fracture width, fracture spacing, if you like, fracture intensity, fracture connectivity, and the presence or absence of mineralization in those fractures. So if we look at all styles of fracture, natural fractures in the subsurface, and this comes out of Nelson's classification, we have open fractures, as we can see in the Dundee Formation. We have deformed fractures, where a deformed fracture is not really a formal specific term in the way a fault or joint is. Rather, we're looking at what generally describes an existing fracture that's undergone some subsequent change in its shape, its orientation, or its character due to later geological overprints, typically tied to newly imposed tectonic stresses or to changing temperature and pressure regimes associated with the burial environment. Then we have deformation bands. These are much more common in sandstones than they are in carbonates, but a deformation band is a narrow tabular zone of localized strain that typically forms in porous granular rocks. As I said, typically in sandstones rather than limestones, but also where we've got crystal development. It can form in limestones as well, where we see grain reorganization. So often we'll see rolling of those particles rather than a single discrete fracture surface. So it's a band of deformation rather than a single breakage. Where grains are broken, we see a band of deformation running through that rock. It's a key mechanism by which rocks in the diagenetic realm accommodate stress if they are porous and granular. Then we have extension fractures. In this case, we're looking in this diagram at an extensional fracture with inoscillon precursors to a shear fracture. Often we'll see cementation along the slippage surface in a fracture. We call them slicken lines or slicken sides on a fault plane. We'll also see varying degrees of mineral-filled fractures, and here we can see a calcite-filled fracture. And in the Ladam Formation, we can see partially open calcite-filled fracture, and also a still partially open fracture filled not by calcite, which is a very common cement in the subsurface, but by blocky anhydrite. We can also have isolated vugs, in this case in a karstic limestone, or we can have touching vugs where the fractures connect up to one another and we have extensive preferential flow directions in that rock. Fractures and the degree of openness of those fractures will influence any rock's permeability. And the important things to look for when we look at what's going to influence the permeability in that carbonate rock are connectivity, the degree to which the fractures are interconnected. That's going to give us a good estimation of the overall flow efficiency. We also have to consider the matrix adjacent to that rock in terms of storage capacity for that reservoir, but in terms of flow efficiency, if we have open fractures, typically the highest permeability will come out of those fractures, not out of matrix drainage. We also have to consider aperture, which is the size of the opening, the physical width of the fracture, which is critical. If we have high overburden pressure or confining stress, that will tend to reduce the apertures in all the fractures, and that will reduce the fracture permeability. Fractures are typically oriented. Doesn't matter whether they're derived from joint sets or they're derived tectonically. We'll see an alignment of fractures relative to the direction of fluid flow, quite often relating to the regional stress field, giving us a strong directional dependence in carbonate reservoirs where fracture is a significant component to the fluid flow. This is sometimes called anisotropic permeability. Then, of course, the type of fracture is also critical. We can have shear fractures or we can have extensional fractures. Shear fractures tend to be more pervasive and provide a more connected system and enhance permeability compared to simple extension fractures. And we'll get back into this when we look at the local development of fracture systems in the next video chapter. We also have to consider with carbonates, not so important in sandstones or shales, but in carbonates we have to consider the degree of diagenetic alteration, both within the matrix, but especially within the fracture itself. The degree of dissolution, the openness created by dissolution, or the degree of cementation, the loss of that fracture conductivity via cementation. This is distinctive and significant in carbonates because they are so chemically reactive. We compare and contrast two features. Dissolution, where we have some type of acidic water seeping through the fractures and dissolving the carbonate along that fracture and so creating fissures, which will create increased permeability. This, of course, then allows more fluid to move through that rock, so it creates a positive loop where increased flow leads to enhanced dissolution. Then we have to consider the loss of permeability in that fracture, the degree of cementation. All open fractures in the subsurface tend to be closed by cements in portions of the fracture network. Cements plug the pathways, and so they reduce or eliminate fracture permeability. The presence of calcite or other mineral fields, anhydrite, dolomite, and so on, determines whether or not a fracture is conductive in its fluid flow. We also have to think about fracture timing. Now, we know that fracturing is particularly effective and common in carbonate reservoirs because they tend to be brittle relative to the intercalated, ductile and sheared evaporites or finer grained shales and mudstones with which they are often interbedded. Now, fracturing can take place at any time during the subsurface history. It can start off with shallow burial and early lithification. It can also be associated with faulting, folding, differential compaction, collapse into zones created by dissolution of evaporite units, via exposure to hydrothermal pressures, via exposure to halokinetic stress regimes, as we talked about in a lot of detail in the reservoirs associated with halokinesis, and also in the sedimentary copper deposits associated with halokinesis. And of course, that very well-known response in overpressured zones of hydraulic fracturing, which we utilise anthropogenically to enhance permeability in units such as the Marcellus Shale, but also occurs in natural situations as well. So when we're looking at fractures in carbonates, We have to look at systems which are typically filled or partially filled with a variety of mineral species, ranging across calcite, dolomite, and hydrite, various sulfide minerals such as galena and sphalerite in ore deposits, along with celestite, strontianite, and fluorite, which we talked about in the base metal association. In most subsurface carbonates, the carbonate cements, the calcites and the dolomites, tend to dominate over those other mineralogies. Fracture fillings can be cementing up a fracture even as the fracture is acting as a fluid conduit. This is often an ongoing process of opening the fracture, cementation, and it can pulse a number of times while flow is active in that fracture. We often map this using techniques such as cathodoluminescence in the cements or the partial cements in open fractures. We can also have catagenic CO2 degassing occurring during pressure release associated with faulting and fracturing. We talked about this in the carbonate diagenesis section, and that can release extensive, almost instantaneous calcite and dolomite precipitates within the fracture system. A lot of late carbonate fracture fills are associated with hydrocarbon stainings or hydrocarbon inclusions, or even solid bitumens, along with saddle dolomites and calcite spars. Infills in those fractures can be multi-stage, as we can see in this fracture, which is now completely cemented by a combination of calcite and siderite. And here we have a fracture with bitumens, tars, blocking up the remaining porosity in that now largely sealed calcite cement in that fracture. That open vug, when it formed, was created by the differential movement, the displacement, if you like, creating a tensional jog, a releasing jog, where that rock then fractured and opened up. It appears now that it's completely blocked by a combination of cement and bitumens. Open fractures make reservoirs. Open fractures are defined as those fractures in a carbonate host that have not been deformed or plugged with tectonic gouge or cements. So permeability, if we don't see a lot of cements in that fracture, is going to be determined by the fracture width, its roughness, and its orientation with respect to the plane of the fracture. The fracture width, as we'll see in the next chapter, the fracture width, its roughness and its contact area along the fracture wall are usually determined by the texture of the host rock, that is, by its constituent particle sizes. If fractures remain open, we increase the permeability in the direction of the fracture plane. But typically, there is little change in permeability in a direction perpendicular to the open fracture system. This is why many carbonate reservoirs have strongly directional drainage in the subsurface, and we have to be very aware of that in terms of maximizing drainage efficiency. We want to drill typically orthogonally to the open fracture network. Because we see ongoing diagenesis, fractures in carbonate reservoirs can be unrelated to the original deposition or even the early diagenetic rock properties, as many of the subsurface fractures we see have been produced by mechanical stresses that came in and affected that rock after it was lithified. When we have these later stage fractures, typically tectonically induced, or maybe dissolution induced, or maybe salt flow induced, the depositional and the diagenetic processes have long since been over by the time these later fractures are forming, and even those fractures can be overprinted by later dissolution and cementation events. So fracturing in the subsurface is not a simple single-stage process. It's a multi-stage process, and often it's a multi-directional process. We're going to sometimes link subsurface fractures to any residual depositional and early diagenetic porosity. So if we have that combination of residual depositional and early diagenetic properties overlain by a later fracture system with open fractures, we're creating a system which is known as hybrid porosity. And we'll talk about the dual nature of porosity and permeability in many carbonate reservoirs later when we look at a series of case histories. Diagenetic fracture hybrids are easily confused with fractured reservoirs. Without sampling, without cores or image logs, it's difficult to differentiate diagenetic fracture hybrids from pure fracture systems. But of course, the response in terms of reservoir production is going to be quite different in those two scenarios. If we have vuggy, cavernous, channeled, or otherwise connected dissolution diagenetic porosity, you see petrophysical and flow responses that will mimic pure fracture porosity and permeability. You always need to suck it and see. It makes it quite difficult to separate hybrid porosities from purely fractured reservoirs without some form of direct observation of borehole through the cores or image logs, FMI or borehole acoustic logs serving that purpose. When we take sidewall cores, we can't sample mesoscale fractures. We can sample microfractures with a sidewall core, but there's a lot of artifact creation when we look at sidewall cores, and whole core sample is a much more effective way to develop a model of a fracture system, as we'll discuss in the section where we're looking at separating natural fractures from artifacts. More than one generation of fractures can be present in a single reservoir, but most will be closed by cement or gouge or compaction. Typically, when we look at a reservoir system in a carbonate, one fracture set, typically the one oriented parallel to the maximum stress under present-day conditions, will tend to remain open and tend to have the greatest influence on reservoir behavior. Within that framework of fractures affecting reservoir, we have a spectrum. At one end of the spectrum, the fractures will contribute the bulk of the reservoir porosity and permeability. These are known as type 1 reservoirs, as we'll see later in the case history study. While at the other end, they may be cemented and acting as impediments to flow, and so we'll see that system known as a type 4 system. And we'll come back and look at these different fracture styles and case history, production histories in the last module. As well as fracture systems, we have this overprint where we see some movement across the zone of displacement. These define shear zones. So a shear zone is a tabular to sheet-like planar to curved planar zone composed of rocks that are more highly strained than the rocks on either side. So typically a shear zone is a type of fault. But because it's a zone, not a single surface of breakage, it's quite difficult to put a distinct fault plane into a shear zone. Within that shear zone, we can have a lot of differentiation related to much more intense foliation, deformation, and folding. Within shear zones, we often find echelon veining or fracturing, and so we don't see a consistent variation in permeability. Shear zones in carbonate rocks would typically function either as a fluid conduit or as a fluid barrier, depending on the specific rock properties, the deformation mechanisms, and its diagenetic history. We'll look at that in the next couple of chapters. So if we see increased permeability with the shear zones acting as a conduit, this is typically in situations where we have low permeability carbonate host rocks, the finer grain rocks or the well cemented rocks, where the brittle deformation of those rocks creates open fractures and breccias within the shear zone. This tends to enhance the permeability by several orders of magnitude and facilitates drainage of that adjacent low permeability matrix. In situations where we have later karst development along what is a faulted core or a shear zone, we can open up that porosity and permeability. We see this in some of the buried hill reservoirs in China that we'll discuss toward the end of this module. Then we have shear zones which act as a zone of decreased permeability or a barrier, where shearing has led to grain crushing, cataclasis, and the formation of fine-grained fault gouges, so reducing the porosity and permeability across that shear zone. So the key factors here, the final permeability in a shear zone, is frequently heterogeneous, and we should always keep this in mind when we're developing fracture models. Fractures are typically not homogeneous in terms of their permeability distributions within the fracture. The style of shear is controlled by fractures, the initial porosity, the intensity of deformation. In other words, we're comparing systems which have shown extensive cataclasis versus open fractures, and secondary processes, especially important in carbonate reservoirs, cementation, stolidization, and dissolution. So here in the noonday dolomite, we can see an extensional shear zone or shear fracture. And we'll come back and look at this style of deformation in a lot of detail in the next chapter. In general, shear zones and the associated fractures and fissures host ore deposits, base metal deposits, as they become foci for hydrothermal flow in both orogenic and halokinetic belts. We looked at that in detail in the sedimentary copper course and discussed the timing in a lot of detail. Further development of a rock into the metamorphic realm means that in metamorphic lithology, shear zones can supply retrograde metamorphism from a peak metamorphage assemblage. Quite often, shear zones in metamorphic rocks are metasomatized. And we'll get into that discussion toward the end of this module. The next section, we'll look at the different types of fracture that develop in carbonates.